Hello, welcome to our video on continuity of a function. Now, in calculus, continuity is a fundamental concept that helps us understand how functions behave. Now, what do we mean here when we say a function is continuous? A function is continuous if it can be drawn without lifting the pen from the paper. But what does that really mean? In this video, we will explore the definition of continuity and learn how to determine if a function is continuous at a given point. We will also cover the three conditions for continuity and work through some examples to illustrate the concept. So whether you are a student looking to ace your calculus exams or just someone curious about math, this video is for you. Now, let's bring the definition of continuity of a function in layman's understanding. Now, as I said earlier, continuity of a function is a concept in mathematics that can be understood in simple terms. Imagine drawing a graph. So think of a function as a graph that you can draw on a piece of paper, and that a function is said to be continuous if you can draw a graph without lifting your pen from the paper. No gaps or jumps. So in other words, a continuous function is one where the graph has no gaps, the graph does not have gaps or jumps or breaks. You can just draw the graph smoothly without any interruptions. Now let's use real life examples to illustrate this concept. Now suppose a ball is rolling down a hill. The ball's motion is continuous as it doesn't suddenly jump or stop. Again, let's consider a river flowing. The river's flow is continuous as it doesn't suddenly stop or change direction abruptly. Also, a temperature graph. A graph showing the temperature over time is also continuous as the temperature changes smoothly over time. Now the question is, what happens when a function is not continuous? On the other hand, a function is not continuous if there are gaps or jumps or breaks in its graph. For example, a ball that suddenly stops or changes direction abruptly, or a river that suddenly dries up or changes course. Also a temperature graph with sudden spikes or drops. So in conclusion or in summary, we can say that continuity of a function means that the function's graph can be drawn smoothly without any gaps or jumps. It's a fundamental concept, as I said earlier on in mathematics, that helps us to understand how functions behave. So now, given that the graph of a continuous function can be sketched without ever removing the pencil from the paper, and that an open circle means a gap in the function. So now let's draw a function. Suppose we have a function, and we have our y, which is f of x, and also we have our x here, and then we have our y equals to 2. So if you have a function here, and then, this is 2. So let's say we have a function, a graph drawn here. We draw this one well. Okay, so now what do we see here? Now we can see that it is clear that the f of x here, the function is discontinuous at the point x is equal to 4. So it means that at the point where x is equal to 4, there is a break or there is a gap. So any function with a break or a gap or a jump is discontinuous at that particular point, or else is continuous. So a function without break or gap is continuous at that point. If there is a break or a gap in that function, then that function is continuous. So in this particular graph that you see over here, It shows that the function is continuous at where x is equal to 4, and that there is a suddenly break or a sudden breaks or jumps in that area. All right. Now let's look at an example here. In this example, we are to show that the rational function f of x is f of x, which is equal to x plus 1 on x minus 2, is continuous at x is equal to 3. Now, in this solution, we are going to look at three main conditions. The first one is that, the first condition, if the function is continuous, then it means that there is a function which is defined at x is equal to 3, or the function is defined at x is equal to 3. So the function is defined at x is equal to 3. Okay. Then the next thing to check is you check the limits of the function as x approaches 3 or approaches 3. So the second thing that we check is we check the condition 2, which is the limits of the function as x approaches 3, or we check whether the limits of the function as x approaches 3 exist. And then the third condition is that if the first and the second condition are equal. So with the first condition, where the function is defined at 2, or the value of the function is defined at 3, if the result of this is equal to the limit as x approaches 3 of that particular function, then it means that the function is continuous at 3. So in this case, we will say that the function as it defined at 3 is equal to the limits of that function as x approaches 3. So if these three conditions are satisfied, then it means that the rational function is continuous at 3. Okay, so now let's check this. Now with the first condition, is the function defined at 3? Now in this case, what we will do is that we just substitute the value of x into the function. In this case, we are finding the value of y as x is equal to 3. If such thing exists, now when we substitute, we are going to have 3 plus 1 on 3 minus 2, and that gives us 4 on 1, which is equal to 4. So now the first condition is satisfied, meaning that the function is defined at x equals to 3. Now the second condition is to find the limits as x approaches 3. Now for the second condition, what it means is that if the function is the function is approaching from the right, is equal to the function as it approaches from the left. And so if x is approaching from values of 3 which are slightly greater than 3, is the same as the value of x uh, as is greater than as is slightly less than 3. So if the function is approaching from the right of 3 or from numbers which are slightly greater than 3, the results will be the same as it approaches from um, numbers which are lesser than 3. So the 3 and the plus here doesn't mean numbers which are greater than 3, but what it means is that if the function is approaching from values of x which are slightly greater than 3, is the same as the function as it approaches from the right when x is slightly lesser than 3. Okay, so now let's check it. When when the function is approaching from the right, we are going to substitute the values of x into the function. So in this example, when when the graph is approaching from the values of the x which is slightly greater than 3, then the denominator is being increased by 1. But when it is approaching from the right, which is slightly lesser than 3, the denominator is being reduced by 2. So now let me take it again. As x approaches 3 or approaches from values of 3 which are greater than 3, then it means that f of x, the denominator of the function becomes 3 plus 1, and that gives us 4. And then the denominator also approaches 3 minus 2, that gives us 1. So the limits of that function, which of course this one is equal to 4 on 1, and that is equal to 4. And so the first condition and the second condition is satisfied. Now for condition 3, when the function is defined as x is equal to 3, it should be equal to the limits of that function as x approaches 3. And since we have all the answers to be equal, it means that f of x or f of 3 is equal to the limits of the function as it approaches 3. So the result that we had for the two are all equal, and that you can see that this function is continuous at 3. This function is continuous at 3. Okay, limits of a piecewise defined function. Now, limits of piecewise defined functions are functions defined by different formulas on different intervals. But how do we find the limits of such functions? In this video, we will learn how to evaluate limits of piecewise functions and explore some common pitfalls to watch out for. We will cover the different types of piecewise functions and work through some examples to illustrate the techniques. And so by the end of this video, you'll be confident in your ability to find limits of piecewise functions, and you'll be one step closer to mastering calculus. Now, when we talk about piecewise defined functions, a piecewise defined function is like a function which has been broken down into pieces. So the function has been broken down into different parts, but it's the same function. Okay, so now we have a function f of x which has been broken down into 3 pieces. And then the first one, we have 1 on x plus 2 as x less than negative 2. And then we have the second one, x squared minus 5. X is greater than negative 2, but x is less than or equal to 3. And then the last part of this same function is root of x plus 13 as x is greater than 3. In this question, we are asked to find whether f of 3 exists. Does the limit x as it approaches 3, f of x exists? And is f of x continuous at 3? If you recall, we said that if a function is continuous, then 3 conditions must be satisfied. And that in this case, the f of 3 as it defined at 3, the function should exist. And as it approaching from the right of 3, that is numbers which are slightly greater than 3 should be equal to, or we should have the same answer as the numbers also approaching from the left of the function, numbers which are slightly lesser than 3. And we have these two conditions to be equal or be the same, then it means that the function is continuous at that point. So in this case, the first question, does f of 3 exist? Or is the function defined at 3? Or the value of the function is defined at 3? So when we check the first question, in these conditions or this range or domains, which one of them is x equals to 3? So when you check the first part of the function, x is less than 3, so this one does not satisfy our first question. Then we check the second one, x is greater than negative 2, but x is less than or equal to 3. So you could see clearly that among the 3 parts of the function, and then the last one, we have root of x plus 13, and x is greater than 3. So among these 3 parts of the function, you could clearly see that the second one satisfies our first condition, where x is equal to 3. and that the function that we are going to use is f of x, which is equal to x squared minus 5. So the function f of x is equal to x squared minus 5 when x is equal to 3. So now let's substitute the value of x into the function. And so we are going to have f of 3 equals 3 squared minus 5. And that gives us 9 minus 5. And that gives us 4. Now we check the second question. Does the limit x axis approaches 3 f of x exist? In this case, we first check the limits of the function as x approaching numbers which are slightly greater than 3. So as I said earlier on, the 3, the positive sign in front, the positive sign at the exponent part of 3 doesn't mean positive 3, but rather it means that numbers which are slightly greater than 3. Great. So when we check our functions, now we go back to our piecewise functions. So at what condition or range is x slightly greater than 3? So when you check the first one, we have x is less than -2, so this one is not part. Then we check the second one too. Sorry, x is greater than -2, x is less than or equal to 2, so this one too will not satisfy because x is less than or equal to, but we want values of x which are slightly greater than 3. So you could clearly see that the third one, which is x is greater than 3, satisfies the first condition of numbers as which are slightly greater than 3 as we approach the graph approach from the right. In that case, we are going to use this function f of x. So the limit as s approaches from numbers which are slightly greater than 3, then we are going to substitute that into that last part of the function, which is root of x plus 13. And that we are going to have root of 3 plus 13, and that gives us root 16. The final result is 4. Then we check the graph as it approaches from the left, and that's the limits of the function as s approaches numbers which are slightly lesser than 3. So that one we check through our piecewise functions again. Of which of these domains is x lesser than or lesser than 3? So when you check this one, x is less than -2, so this one is not satisfying our condition. Then we check this one too, x is greater than -2, x is less than or equal to 3. And then the third one is x is greater than 3, so this one too is disqualified. And now you could clearly see that it's the second part of the piecewise function that satisfies this condition. And now we are going to substitute the limits as s approaches from the left, great numbers which are slightly lesser than -3. And then we are going to use x squared minus 5. And that gives us 3 squared minus 5. And 3 squared minus 5 is 9 minus 5. That gives us 4. So you can clearly see that the function, the graph as it approaches from the right is equal to the function as it approaches from the left. And that f of x exists, or the limits of the function as it approaches from the left, f of x exists. And for the last condition, since f of x equals to the limit as s approaches 3, f of x exists, then it means that this function is continuous at 3. So this particular question is being solved here. In this question, we are to talk about continuity on an interval, and that we have a question of which we are to show that the function f of x equals 1 minus root 1 minus x squared is continuous on the interval -1, 1. Now let's break this one step by step to determine if the function f of x is equal to 1 minus root 1 minus x squared is continuous on this interval. So the first step is to check the domain, and that the expression under the square root must be non-negative. And so 1 minus x squared should be greater than or equal to 0. So solving this inequality gives us 1 is greater than or equal to x squared, or x squared is lesser than or equal to 1. Now, when we solve this, we could clearly see that we are going to have x squared is less than or equal to 1. And so when we take square roots on both sides, we are going to have positive or negative. Let me rewrite this one well. So I have x squared lesser than or equal to negative, positive and negative 1. And that we can say that x is greater than or equal to 1, but x is less than or equal to 1. So x is greater than or equal to negative 1, or x is less than or equal to 1, which matches the given interval, of which we have this one here. And therefore, the function is defined throughout the interval negative 1, 1. Then the next step is to check for continuity at the interior points. So for x in the interval negative 1, 1, the function is composed of continuous functions, that is polynomials and square root functions. In that case, since 1 minus x squared is greater than 0 for x in the interval negative 1, 1, then the square root is also defined and is also continuous. Therefore, f of x is continuous at every point in negative 1, 1. Now, step 3, we check for continuity at the endpoints. So at x equals negative 1, f of negative 1 as defined at that particular function, at that point of the function, then we are going to have 1 minus, into brackets, 1 minus negative 1 squared. So we are going to have 1 minus root 1 plus 1, and then we're going to have 1 minus root of 2. Okay, and that's, we have negative, here we are going to have negative 1 times 1, so we are going to have positive 1, and 1 minus 1 gives us 0. So in this case, we are going to have our final answer to be equal to 1, for the square root of 0 is 0. In this, therefore, now we check also at x equals to positive 1, or we check from the left to as the function approaches from that side. So we substitute f of 1, and that we have 1 minus root 1 minus 1 squared. So this gives us the same answer as 1 minus root of 0, and which is equal to 1. And so since the function as it approaches from the right is equal to the function or the graph as it approaches from the left, the function is continuous from the right at x is equal to, the function is continuous from the left as it's equal to 1, and it's also continuous at the left as x is equal to negative 1. So it means the function is continuous. So since f of x is continuous at every point in negative 1 and 1, then continuous from the right as x is equal to negative 1, and continuous from the left as x is equal to positive 1, then we conclude that the function f of x is equal to 1 minus root of 1 minus x squared is continuous on the interval negative 1, 1. Thank you, and don't forget to subscribe to our channel.